In my last video, I had my giant oscilloscope sitting on my desk here, and after I did that, I was like, I remember seeing some portable oscilloscopes like this one on Matthias Wandel and I think Bronchus Creations and a couple other channels. I've seen these before. And I thought, back when I used my power drill that I plugged into the wall and I switched to a battery-powered drill, that was kind of life-changing for the projects that I did. And so I thought, maybe that's the time to try one of these guys out. So this is a FNIRSI 2C53T. This is their like portable oscilloscope. I bought this thing. This is not sponsored. They didn't send this to me or anything like that. But I thought it might be time to actually try using one of these things out. And I did, and it's actually really nice. It's not anywhere near a desktop oscilloscope with all the knobs and buttons you get. You can't get to the settings and things that you want as quickly, but this is on my desk and I can use it anytime within about 5 or 6 seconds. It starts up pretty quickly. You choose the function. I'm not going to get into the signal generator or the voltmeter, just the oscilloscope on here. But it does come with probes for a voltmeter. You can see the probes in here. It comes with some attachments for the oscilloscope for coloring the channels and a little plastic tuning knob, because the probes it comes with are also pretty decent. They have the ability to tune. It does times 1 or times 10, 100 megahertz probes. This is a 50 megahertz oscilloscope, so these are specs that you don't really need to care about too much if you're new to oscilloscopes and electronics. This does 2 channels, which I really wanted because one of the things I like to do is compare 2 signals to each other, and that's especially useful for timing. So today, just to show this thing off really quick, I'm going to put in 2 channels, but I'm going to have one channel on my clock over here and another channel on a rubidium frequency standard that's a GPS disciplined oscillator. Now, a lot of people are asking me, like, why do you build these clocks? Why do they need to be so precise? All that kind of stuff. There's actually a lot of use cases for it. One of the things that I actually am working on a video for this right now is there was a Blues hockey game, which I'm wearing the shirt right now, and the hockey game, they had 4 sets of clocks. Actually, well, 3 sets of clocks. Each one was redundant, so they had 6 master clocks that were all synchronized with PTP and had a failover clock server, all these kind of things, because all the video equipment needed that timing. It needs precise timing for video transitions, all that kind of stuff. So that's one of many use cases. There's also financial stuff that you can do, database transactions. There's infrastructure things for the power grid frequency. Having a stable frequency is very important for that. Anyway, the point of all that is to say there are use cases for this stuff. Nothing that I use it for, but I still like learning about it all. I was impressed. This is the reason I'm making this video. I was impressed by this little guy's ability to get down to the nanosecond level. And I'll show you what I mean. So first, to go over the testing setup, I have my clock here that's running on a Raspberry Pi Pico. It has a GPS module inside of there. The GPS antenna feeds in through this wire. That comes from a GPS antenna that I have outside the building. And it goes through a distribution block here and one in the back. And I am on pin 16 on the Pico, which has a PPS output, and the ground wire is attached to a ground on there as well. And then this is a Calnex GPS DO, and it has its own GPS antenna input, so that's coming from the same GPS antenna out back. And you might hear that it's a little bit loud. That's because it has a fan inside of it. And it says RB/GPS because it has a rubidium oscillator inside, which if it loses the GPS signal, it can still have a very stable output for a very long time. It can be down to, I forget what the exact spec is, but like that way, if you lose GPS signal, like if there's jamming or if you have a bad antenna location or the line gets cut or whatever, you still have a pretty good frequency reference. It also gives you 10 megahertz output, which we might check that too. But anyway, I have its 1 PPS output coming through this wire. This is just a BNC cable that goes from here to there. And then I have the probe coming over here. So I'm going to put them both into here. I'll put the stable PPS from that guy onto here. And I'll put the probe from my clock into here. And one thing that I do think is a little annoying is these connections up here. Like they're recessed, which is fine, but it also makes it a little bit annoying and hard to tighten them up, especially if you have multiple channels on here. This is channel 1, channel 2, and then this is the frequency generator output. So one nice thing is this is all battery powered, so I didn't have to bring over a power cable. I could bring this in my car with me and check things in the car, whatever. It doesn't matter. The battery seems to last at least a couple hours. I've been doing this, I haven't charged it since the first time I charged it, and I probably used it for 20 minutes before, and you know, the battery still says it's full. I don't know. Don't quote me on any battery specs. The one annoying thing about this guy is because there's not a whole lot of surface area for buttons or knobs, everything is through like these 4 buttons that controls all of the different things on the screen. And then there's like up, down, left, right, and play, pause for triggering. And then you can set your channel options. So you can turn it on or off, say if it's by 1 or by 10, DC or AC coupling, and FFT transform. So that's for each of the channels. It has the same kind of settings there, and you can get in and out. Most of the settings are easy enough to get to, but sometimes it's a little confusing. Like right now it's on, I can change the voltage. It's not always exact. Okay, so this is voltage per division. So right now this is 2 volts per division for the yellow line, but then it took me the longest time to figure out how to get, like if I want to change this voltage, it's yellow right now. But I think if I hit this, yeah, that changes to blue. So now I can change the blue line, see its voltage per division. So you can change those independently. I'm going to set them both onto 5 volts for now. And if I hit play, so this is where I can compare these 2 signals. I have a trigger set up for when this signal goes above like 2 volts. And this is going up 5 volts, so it goes up 5 volts. So halfway between there, it triggers and catches that when there's a rising edge on the signal. And we can zoom in using this. You can see this time reference changes up here. And that's saying that this is 200 nanoseconds per division. So each of these little squares is 200 nanoseconds. So I'm going to zoom right in on here. And we can see that in 10 nanoseconds, we're less than 10 nanoseconds different between these 2 signals. So this is just one capture though. If I hit it again, I'm going to get another trigger. So now we're about 20 nanoseconds, 24 nanoseconds, something like that. 25, maybe 30 there, 30 again, 25. So if I keep triggering this, you'll see that we're kind of walking up and down 20 to 30 nanoseconds. Now, one thing that's interesting about that is if we look at the antenna cables here, so here's the antenna cable for this. It comes up here, and it comes down here to right here. This is maybe 7 or 8 feet of cable. The other cable is here, and do you see that little bundle of wire right there? So that bundle of wire, the wire coming from this antenna signal over to here is probably 10 feet longer or 8 feet longer than the cable that's coming to here. So that could be accounting for that 20 millisecond delay there. It might be, but the bigger point that I have is though this is consistent. Well, I say that, but now it's even a little more consistently off by like 50 to 100 nanoseconds. So one thing that I wanted to find is how accurate is this clock really, or how accurate could I make it if I train the internal RTC on the Raspberry Pi Pico off of the GPS signal. And it's not going to be as good as a multi-$1,000 rubidium clock standard reference, but it's pretty good. We're talking less than 100 nanoseconds. So anyway, I thought it was kind of cool to test this guy out on this because I didn't expect it to be that good and reproducible for the nanosecond realm, but it is. And this is, I think it's 50 megahertz, 250 megasamples. Those specs aren't incredible compared to my other oscilloscope, but this is like as good as the oscilloscopes I was looking at 5 or 10 years ago last time I bought one for my desktop. So yeah, it's not bad. And I think this is only 80 or 90 bucks, which is a steal compared to the other oscilloscopes I've been looking at. The one big advantage is if you get a bigger oscilloscope, you're going to have knobs and buttons that get you into settings a little quicker. But for the basic things, this is not bad at all. I forgot to mention that I have finally gotten that transparent PLA. This is transparent black PLA, and it's actually a lot more transparent than I thought it would be. But I printed these two out, one with a 0.2 millimeter layer and one with a 0.4 millimeter layer, so 2 layer heights basically. and I tested it against this car UV window tint, and you'll see that the thing that I finally went with is the tape. This is the tape from Paper Street Products. They make it in all kinds of colors. This is their gray tape, and I just stuck one layer of that on there, and it looks great. So I think that's the solution I'm going to stick with. Well, I said I wasn't going to do this, but I am. I want to see how the signal generator on here works and if it's any good. So I just turn it on and I go to signal generator, and we can pick a different signal. And I'll just use the same BNC cable that I was using over there for the GPS. For the output, this says DDS. I don't know what DDS stands for. Here in the US, that often is the acronym I see behind dentist names, DDS. But I'll put it into channel 3 here. And we'll turn off channel 1 and turn on channel 3 and hit auto. And let's see what we get. So we do have this waveform. So if you've never used an oscilloscope, the nice thing is with this one, I have all these knobs. Let me zoom in so that you can actually see what I'm seeing. We have the signal generator. It's doing a sine wave, frequency of 1 kilohertz, it looks like, an amplitude of 3 volts. So we can see on here, I have, let's see, it's saying the frequency. Why are those two on there? So I moved this over to channel 1 because I don't know, this oscilloscope is way beyond my pay grade. This was provided for a project that I was working on and am still working on, and this is more of my pay grade of oscilloscope. But anyway, I don't know how to get channels 3 and 4 into this little graph here, but you can see that this is measuring the peak-to-peak frequency of this, which it's hovering around a kilohertz. This is saying it's 1 kilohertz, and this is a pretty good connection. So this is not the most perfect clock, the most perfect oscillator inside that's providing these waveforms, but I can zoom in on this, and we can see that there's actually stair-stepping. So what that means is that the little ADC chip in here, whatever function that they're using to provide this waveform, is kind of like step, 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 step. And that's something that happens in electronics. You know, you pay a lot more money to get a perfect sine wave, but you can see that there's definitely steps in here. And then let's try some other things here. Square wave. So there's a square wave, and that's a pretty good hard line there. So good job on that one. I think it's a little easier for a digital device to put out a square wave. And a sawtooth wave. We'll probably see, yeah, there's those steps in there as well. Let's see what else. We got a half wave. And there you go, you got those steps again. Full wave, so that's like a little hillside. A step wave, and this is where you actually do need steps. There they are. And reverse step wave, so going backwards. Index up, so going up, and there's those steps again. Index decrease, and we can see those stair steps again. And direct current, so this is just outputting DC, and you can see this is 1 volt between these divisions, so that's 3 volts exactly. And on here it says 3 volts, so that's good. Audio, so it's just giving that, but you can see there's those steps again. So we're definitely not getting like a perfect, beautiful form here. Lorentz waves. So all of these work, and if you just need a signal to test something, this is going to give you that. So I'm happy enough with that. And then if I want to change these, so I'm looking in the interface here, and I don't know how to change these things. So if I hit select maybe, move, nope. Menu. Oh, here we go. So you hit play, and then I guess you can change the frequency. Oh, here we go. We'll go to 2 kilohertz, 3, 4. So yeah, that is working. Oh boy, we can do 1 hertz. So this is once per second. Okay, so there's 1 hertz. And if we look down here, once this comes across, we should start seeing 1 hertz, I would imagine. It's doing 2 hertz, that's interesting. What if I go to, I'll go to 10 hertz and zoom in a bit. So 10 hertz is working here, but if I go down to 9 hertz, we're still showing 9 hertz up here. Oh, there we go, 9. We'll go down to 8. Okay, we're at 8. If I go all the way down to 1 hertz, Let's see if this picks it up. It's interesting, it won't go down below 2. Let's try 2 hertz on here and see if that stays at 2. Yeah, so that's kind of funny. This is this lets me go down to 1 hertz, but it's not reflecting on here. It's still at 2 hertz. If I go up to 2 hertz, it stays the same. You can see that visually. So 3 hertz does make a difference. So here this should go up to 3. There you go, 3 hertz. So it looks like this goes down to 2 hertz, not 1 hertz. Just something funny and interesting to see. We'll do a square wave. How do I get out of here now? Menu, there we go. We'll do a square wave at 1 hertz and see what that says. See, this is a square wave, still saying 2 hertz. So I think that this is actually 2 hertz up to whatever the highest rating is on it for the signal generator. So if you wanted to get a 1 hertz signal out of this, apparently you're out of luck on that. But the big thing is that when you have this, once you learn how to use this, these knobs are very intuitive. You can get around into things. You can zoom in and out very quickly. You can show part of the scale or the whole scale. You can zoom in on just a part of it. You can save things off to a USB drive here. You can, this one plugs into your network and it has an HDMI output, all kinds of cool things. This one doesn't have all that stuff, but it's extremely handy. This one is very annoying to carry around if you're trying to go portable, but it's great for a desktop. This one, I could fit this in my pocket. It wouldn't look very good, but I could do that. Yeah, so there's your little bonus testing the signal generator on here.